Perhaps these missing galaxies are still hidden to diffuse for our instruments to reveal. Perhaps the simulations themselves overestimate how many small dark matter halos should exist. Another possibility is deeper still. Our picture of dark matter may be incomplete. One long-standing tension is known as the Corpus problem, which concerns how dark matter is arranged in the hearts of dwarf galaxies. Models predict that dark matter should pile up sharply toward a galaxy's center, forming a dense peak called a cusp. Yet observations often tell a different story. In many dwarf galaxies, dark matter appears spread more evenly, creating a softer central core instead. This mismatch hints that something is missing. It may be that star formation and repeated supernova explosions stir and redistribute dark matter more efficiently than simulations assume. Or it may be that dark matter itself behaves in ways we do not yet understand. It is also possible that sharper observations will eventually bridge the gap between theory and reality. At the heart of these models lies a powerful idea: hierarchical growth. In this view, structure builds upward. The smallest systems form first. They merge into larger ones, which then combine again, step by step, until giant galaxies emerge. The largest galaxies alive today are not pristine creations, but the end products of countless unions. The local group carries the marks of this process. The Milky Way bears long stellar streams, ghostly trails left behind by dwarf galaxies it absorbed long ago. Andromeda's structure is even more complex, layered with different stellar populations that speak of repeated turbulent mergers. These galaxies did not grow in silence. They were shaped by collision and change. For nearly a century, astronomers have known that Andromeda is not drifting away like most galaxies. Instead, it is moving toward us, or more precisely, we are falling toward one another. While cosmic expansion carries distant galaxies outward, Andromeda approaches at roughly 250,000 miles per hour. Current calculations suggest that in about 4 billion years, the Milky Way and Andromeda may collide. There is uncertainty, perhaps only a 50% chance, but if it happens, it will redefine our cosmic home. This will not resemble two solid objects crashing together. Galaxies are mostly empty space. Stars are separated by such vast distances that direct stellar collisions are exceedingly rare. The true violence lies in gravity. As the galaxies interpenetrate, their spiral structures will unravel. Stars will be hurled into new paths. Vast clouds of gas will collide, igniting waves of intense star formation. Over several billion years, the chaos will settle. The two spirals will fuse into a single, enormous, elliptical galaxy already, nicknamed Milkdromeda. Triangulum may be drawn into this dance as well. Simulations suggest it could merge early, later, or even be flung entirely out of the local group, at the cores of both galaxies. Their supermassive black holes will spiral inward and merge. That union will send powerful gravitational waves across the universe, ripples in space-time itself. Meanwhile, the smaller galaxies will face uncertain fates. Some will be ejected, cast into the dark between galaxies. Others will be consumed, their stars folded into the growing giant. A few may endure as satellites, diminished but not erased. Yet this is not the end of the story. Far beyond these events, the universe itself continues to change. Space is expanding, and that expansion is accelerating under the influence of dark energy. Distant galaxies are carried away from us, receding faster the farther they lie. Beyond a certain distance. This recession outpaces light itself, not because galaxies break the cosmic speed limit, but because the space between us expands too quickly. Those galaxies cross a boundary known as the cosmic event horizon. Once beyond it, their light can never reach us again. As acceleration continues, that horizon will draw inward. Galaxies visible today will one day fade from sight forever. Only what is gravitationally bound will remain. The local group is held together by its own gravity. It will not be torn apart by expansion. In the far future, as the rest of the universe slips beyond reach, this small family of galaxies reshaped, merged, and transformed will stand alone in an ever-darkening cosmos. The Milky Way, Andromeda, and their nearby companions are bound tightly enough by gravity that the expansion of space will never tear them apart. But everything beyond this small family will slowly drift away. Over time, Distant galaxies will slip farther and farther beyond reach until they vanish entirely from view. Roughly 150 billion years from now, the only galaxies visible from the merged Milky Way Andromeda system will be the remnants of today's local group. All others will have crossed the cosmic event horizon. Their light will never arrive. An astronomer living in that distant era might scan the heavens and conclude that their galaxy stands alone, no evidence of neighbors. No hint that a wider universe ever existed. In that sense, we are living in a rare moment, a privileged window in cosmic history when the universe still reveals its vastness. When distant galaxies are visible and the large-scale structure of reality can still be studied, future civilizations, if any arise, will not inherit this view. Far beyond that era lies an even quieter future. Trillions of years from now, the stars themselves will fade away. Stars are born from gas, and the universe holds only a finite supply. Once it is exhausted, no new stars will ignite. Existing stars will continue their slow decline. The most massive will burn out quickly, ending in violent explosions or collapsing into black holes. Stars like our sun will swell into red giants, then cool into dim white dwarfs. The smallest stars, red dwarfs, will linger the longest. But even they will eventually go dark. After 100 trillion years, the universe will be cold and lightless. The merged galaxy that once was the local group will be populated only by stellar corpses, white dwarfs, neutron stars, and black holes. No warmth, no starlight. No readily available energy except for the faint, unimaginably slow whisper of Hawking radiation as black holes evaporate. As for life, we still do not know whether Earth is unique. No definitive evidence has yet answered that question. But if life exists elsewhere, where might it arise? Within the Milky Way alone, there are hundreds of billions of stars, and we now understand that most of them host planets. Some of those planets orbit within habitable zones regions, where temperatures allow liquid water to exist on a planet's surface. Liquid water is central to life as we understand it. That alone opens vast possibilities. Extend the view beyond our galaxy, and the numbers grow overwhelming. Andromeda contains roughly 1 trillion stars. Triangulum adds tens of billions more. Even the smaller galaxies contribute millions or billions of suns. If only a tiny fraction host habitable worlds, and if only a small fraction of those worlds ever give rise to life, the local group could still harbor thousands, or even millions of living planets. The basic ingredients are not rare. Water is widespread. Hydrogen and oxygen are among the most abundant elements in existence. Wherever temperature and pressure align, liquid water can persist. Energy is also plentiful. Stars provide heat and light. Chemical reactions release power. Radioactive decay warms planetary interiors. And the elements essential to life, carbon, nitrogen, oxygen, phosphorus, sulfur air, forged in stars, and dispersed across space when stars die. These ingredients are woven throughout the cosmos. The mystery is not whether they exist, but whether they assemble in the right patterns. On Earth, they did so remarkably quickly. Our planet formed about 4.5 billion years ago. And evidence of life appears by at least 3.5 billion years ago, possibly earlier. Life emerged within the first billion years, almost as if the universe, given the chance, was ready to awaken. If life emerges easily whenever the conditions align, then living worlds may be scattered throughout the local group. And if intelligence has arisen elsewhere, a deeper question follows. Could contact ever be possible? The separations are immense, even traveling at light speed. A signal would need over 2 million years to reach Andromeda and millions more for any reply to return. Conversation, in the familiar sense, would be impossible. Within our own Milky Way, however, the cosmic distances are less forbidding. If another intelligent civilization exists here, and if it has discovered radio waves as we have, traces of its presence might already be crossing the stars. Or perhaps our own signals have already brushed past distant minds. This hope underlies SETI's search for extraterrestrial intelligence. Radio telescopes listen patiently, sweeping the sky for patterns that nature alone is unlikely to produce. At the same time, scientists search in a quieter way, examining distant planets for biosignatures, chemical fingerprints that hint at life. Oxygen is one such marker. On Earth, it is continually replenished by photosynthetic organisms. Without life, it would quickly vanish from the atmosphere. If we were to detect unusually high oxygen levels around another star's planet, it would be a powerful sign that something living is at work there. The James Webb Space Telescope is capable of probing the atmospheres of nearby exoplanets. While it cannot peer into other galaxies, it can examine worlds within our own. In the coming years, it will study dozens of potentially habitable planets, searching for water vapor, methane, oxygen, and other telling gases. Should evidence of life be found, it would reshape humanity's understanding of itself. One of our oldest questions, are we alone, would finally receive an answer. Yet even if that answer never comes, the pursuit itself carries meaning. The search reveals how life might arise, how planets differ, and how the laws of physics and chemistry sculpt the universe. Through studying the local group, we have already uncovered profound truths. We have learned, first, that galaxies exist in astonishing variety. Some, like Andromeda, host 1 trillion stars. Others are barely there at all, faint dwarfs containing only a few thousand. This range shows that galaxy formation is not a single path, but a branching destiny shaped by environment and origin. Second, we have discovered that galaxies do not live in isolation. They interact endlessly, merging, colliding, exchanging gas, tearing stars from one another. These encounters drive much of their long-term evolution. Third, we now understand that small galaxies are everywhere, even if many remain hidden. The local group likely contains far more dwarf galaxies than we have yet identified. By tracking the motions of satellite galaxies, astronomers have measured the true mass of the Milky Way, including its invisible dark matter halo. By reconstructing the star formation histories of dwarfs, they have glimpsed conditions in the infant universe. The oldest of these galaxies began forming stars when the cosmos was only a few 100 million years old. Those earliest stars, known as Population 3, were likely enormous, burning brightly and briefly. They ended their lives in violent supernova, forging the first heavy elements and scattering them into space. Later generations of stars were born from this enriched material. By analyzing the chemical fingerprints of stars and ultrafaint dwarfs, scientists can infer what those first stars were like. The local group also reveals the structure of the universe itself. Galaxies are woven into a vast cosmic web, filaments and sheets surrounding immense voids. Our group lies along one such filament, and its gravitational pull subtly guides our motion through space. It also anchors our measurements of the cosmos. Distances to nearby stars are measured by parallax. Those measurements calibrate Cepheid variable stars. Cepheids anchor distances to local group galaxies, which in turn calibrate type Ia supernova visible across the universe. This latter allows us to map the observable cosmos. The local group even preserves clues about reionization, the era when the first stars flooded the universe with ultraviolet light, reionizing hydrogen after the cosmic dark ages. Many ultrafaint dwarfs formed during or shortly after this time, carrying records of the universe's first illumination. When we observe these galaxies, we are always looking backward. The light from Andromeda arriving tonight began its journey 2 million years ago. We do not see it as it is, but as it was. This quiet truth reveals something profound. There is no single, universal now. Time itself is stretched across space. And every observation is a message from the past arriving only now to those who are watching. Across the vast reaches of space, the idea of a single shared now quietly dissolves. This is not philosophical poetry, it is a direct consequence of Einstein's relativity. Time itself refuses to stay aligned across cosmic distances. Yet within this shifting framework, the local group reveals something steady and profound. The laws that govern existence do not change. The stars burning in Andromeda obeyed the same rules as those in the Milky Way. Gravity binds matter there exactly as it does here. This quiet consistency, the same physics everywhere, is one of science's deepest assumptions. And the local group affirms it. In structure, our galactic family is unremarkable. 2 large galaxies dominate, surrounded by many smaller companions. This arrangement is common throughout the universe. Even our position within it carries no special distinction. This ordinariness reflects the Copernican principle, the understanding that we do not stand at a privileged center of creation. And yet, despite this humility, The coming decades promise revelation. New sky surveys will uncover hidden members. More powerful telescopes will peel back detail once thought unreachable. Simulations will trace the local group's past and future with increasing clarity. The Vera C. Rubin Observatory will repeatedly map the sky, assembling a treasure trove of data. The extremely large telescope in Chile will resolve individual stars across the local group, the Nancy Grace. Roman Space Telescope will scan the infrared sky, unveiling populations long concealed. Each instrument will illuminate another layer. Still, the mysteries remain. Why do some dwarf galaxies host globular clusters while others remain bare? What determines whether a small galaxy continues forming stars or falls silent? How much dark matter truly permeates the local group, and how is it arranged? Are faint galaxies still waiting beyond our detection? What form will this system take billions of years after the Milky Way and Andromeda become one? The local group is our cosmic threshold. Through it, we study galaxy formation, dark matter, and the long arc of cosmic evolution. Every observation adds another fragment to a greater design. Every telescope sharpens the picture. Look up with unaided eyes, and you mostly see the Milky Way, but instruments reveal more. The Magellanic Clouds, Andromeda's pale glow, Triangulum, and dozens of quiet dwarfs. Each is an island of stars drifting in immense darkness. Though separated by unimaginable distances, they remain close enough to shape one another, close enough that gravity binds our destinies together. These roughly 50 galaxies are more than distant lights. They form our cosmic setting, the structure that cradles our existence. To understand them is to trace our own origin and fate. That is why the local group matters, not simply because it exists, but because through it we come to know who we are and where we stand in the universe. To see this clearly, one must understand what galaxies truly are. They are not random swarms of stars, but ordered systems with layered histories. The Milky Way, for example, begins with its central bulgidents, ancient sphere of roughly 10 billion stars, compressed into a region only a few thousand light-years wide. Here, stellar crowding reaches extremes. If our solar system were placed there, the night sky would blaze with countless stars brighter than Venus. Radiating outward is the disk of flattened realm, where gas collects and new stars are born. This is where spiral arms emerge, not as rigid structures, but as long-lived density waves, like a traffic jam that holds its shape while cars pass through. Stars move in and out of these arms while the pattern endures. Compression within these regions ignites star formation, giving spirals their luminous beauty. Beyond the disk lies the halo, a vast faint sphere of ancient stars and globular clusters on elongated orbits. These stars plunge through the galaxy before arcing far into space. Encompassing all of this is the dark matter halo, immense, invisible, and essential. Without it, the galaxy would unravel. The outer stars move too quickly to be bound by visible matter alone. Andromeda mirrors this structure, but on a grander scale. Its bulge is larger, its disk richer, its halo scarred with streams and shells, echoes of consumed galaxies. Triangulum, smaller and unbarred, is simpler still. A modest bulge, a clean spiral disk, and a lighter halo. Its clarity makes it a living laboratory for understanding spiral galaxies in their purest form. Dwarf galaxies are simpler yet. Some lack disks entirely, appearing as diffuse spheres of stars embedded in dark matter. Others form stars in scattered clumps, without ordered arms or symmetry. These humble systems are not failures of creation, they are records. In their simplicity, they preserve clues to how galaxies rise, change, and endure. To study these structures is to read the architecture of the universe itself. And for those who are watching closely, the message is clear. The cosmos is vast, ordered, evolving, and we are not separate from it. We are part of the pattern. The galactic disk emerged as in falling gas cooled and flattened into a slow, revolving sheet, while the bulge appears to be a relic of motion and memory stars drifting inward from the disk, mixed with others taken from smaller galaxies consumed long ago. Farther out, the halo tells a quieter story. It is filled largely with stars that once belonged to dwarf galaxies, gently pulled apart, and woven into the Milky Way over immense stretches of time. To uncover these ancient events, astronomers turn to one of their most revealing guides, stellar chemistry. Not all stars share the same ingredients. Some are composed almost entirely of hydrogen and helium, while others carry traces of heavier elements, carbon, oxygen, iron, even gold. This variation exists because the universe itself has been slowly enriched. At the moment of the Big Bang, matter was simple. Roughly 3/4 hydrogen, 1/4 helium, and almost nothing else. The elements that build worlds and bodies did not yet exist. The very first stars known as Population 3 formed from this untouched material. They were likely enormous, dozens or even hundreds of times more massive than the Sun, and they lived only briefly. When they ended their lives in powerful supernova explosions, they forged and released the first heavy elements into space. From this altered gas arose the next generation, population to stars. These stars were no longer pure, though their metal content remained sparse often, just a fraction of what we find in the Sun. As cosmic time unfolded, cycles of birth and death continued, steadily enriching the universe. By the time our Sun formed around 4.5 billion years ago, about 2% of its mass consisted of elements heavier than helium. Though small in proportion, this fraction changed everything. Those elements made rocky planets possible and opened the door for life itself. By measuring which elements stars contain, astronomers can estimate when they were born. Stars with extremely low metal content must have formed very early, before the universe was heavily enriched. Those with higher abundances arose later from gas shaped by countless stellar generations. This is why dwarf spheroidal galaxies are so valuable. Many of their stars show astonishingly low levels of heavy elements, marking them as survivors from the universe's youth. In some ultra-faint dwarfs, stars have iron abundances as low as 1/10,000th, that of the Sun among the oldest known stellar relics. That total metal content is only part of the message. The proportions between elements reveal even more. Oxygen and magnesium are produced mainly by massive stars that explode quickly as supernova. Iron, however, also comes from a slower process, type Ia supernova, which occur when white dwarfs gradually gain too much mass. Because these explosions take longer to occur, iron appears later in cosmic history. In the early universe, before type Ia, supernova became common. The ratio of oxygen to iron was much higher than it is today. By reading these ratios in ancient stars, astronomers can pinpoint when they formed relative to this transition. In this way, stellar chemistry becomes a kind of cosmic scripture, preserving the timeline of star formation and revealing how the earliest chapters of the galaxy were written. The elements locked inside stars are more than raw material. They are testimonies of specific cosmic events. Certain elements, such as strontium, barium, and europium, are forged in moments of extreme violence through what astronomers call the rapid neutron capture process. This process unfolds during neutron-star collisions and in rare, powerful supernova, where matter is subjected to forces almost beyond comprehension. Other elements, like carbon and nitrogen, arise more gently, created in the quiet late-life stages of lower-mass stars as they shed their outer layers back into space. By reading this full elemental inventory, astronomers reconstruct a galaxy's entire history of creation and destruction. Milky Way's halo, in particular, contains stars with wildly different chemical signatures. This diversity is no accident. The halo was assembled piece by piece, built from many smaller galaxies that were swallowed over billions of years. Each of those dwarfs followed its own chemical path, enriching its gas in a unique way. When they were torn apart, their stars carried those chemical identities with them like fingerprints frozen in time. Through detailed chemical analysis, astronomers can group halo stars that once belonged to the same long-vanished galaxy. In this way, they can count how many galaxies the Milky Way consumed, estimate when each merger occurred, and infer how massive those lost systems once were. Even destruction, it seems, leaves records that can be read by those who know the language. Galaxies themselves are never still. Within them, stars are continually being born, living out their luminous lives and dying. To understand how a galaxy evolved, astronomers must determine its star formation history, when stars formed, how rapidly, and under what conditions. Star formation begins when cold. Clouds of gas and dust collapse under gravity. As the cloud contracts, heat and pressure build until nuclear fusion ignites at the core. A new star enters the universe. Yet this process is remarkably wasteful. Only a small fraction often, just 1 or 2% of a gas cloud becomes stars. The rest is dispersed by stellar winds, supernova explosions, magnetic forces, or turbulent motion that prevents collapse. How efficiently a galaxy turns gas into stars depends on both how much gas it possesses and how easily that gas can settle and condense. Large spiral galaxies like the Milky Way and Andromeda form stars at a steady, moderate pace, producing a few solar masses of new stars each year. At this rate, their gas supplies will last for many billions of years. Other galaxies experience brief but furious episodes known as starbursts, during which hundreds or even thousands of solar masses of stars form each year. These bursts are usually triggered by mergers or close encounters that compress gas and ignite rapid star formation. They burn brightly but briefly, ending once the gas is consumed or blown away. Dwarf irregular galaxies occupy a middle ground, though small. They form stars vigorously relative to their mass, and often retain enough gas to continue this process for immense spans of time. In contrast, dwarf spheroidal galaxies are silent, exhausted or lost their gas long ago, and have not formed new stars for eons. Why these galaxies shut down so completely remains one of the enduring mysteries of galaxy evolution. Astronomers decode star formation histories by studying stellar populations. Young stars glow blue and hot, while older stars fade to yellow and then red. By counting stars of different colors and brightnesses, scientists reconstruct the timeline of star birth within a galaxy. This method reveals astonishing variety. Some galaxies formed nearly all their stars early in cosmic history. Others maintained a steady rhythm, and some experienced repeated cycles of activity and dormancy. These histories are deeply tied to mergers. Major collisions ignite intense star formation. Smaller mergers can replenish gas and prolong stellar birth. Isolation allows galaxies to evolve slowly and quietly. At the heart of nearly every large galaxy, another powerful influence resides. Hidden at the center of the Milky Way is a supermassive black hole known as Sagittarius A*. Unlike black holes born from collapsing stars, this object weighs about 4 million times as much as the Sun. Its presence is revealed by the stars that orbit its stars moving at astonishing speeds, some reaching several % of the speed of light. Their motions testify to an invisible force, a silent anchor around which the galaxy itself is bound. Together, these processes element creation, star formation, mergers, and black holes compose a grand, interconnected story. The galaxy is not merely a collection of stars, but a living archive, shaped by violence and grace alike, preserving within its light the memory of everything that came before. By tracing the paths of stars circling these dark centers, astronomers have been able to weigh the invisible and even witness subtle distortions predicted by Einstein's relativity. At the heart of Andromeda, the central black hole is far more imposing. Carrying a mass estimated between 110 and 230 million suns, Triangulum is believed to harbor a similar presence, though its distance and our inability to resolve stars near its core keep that guardian hidden from direct view. The origin of these supermassive black holes remains one of the universe's unanswered riddles. One vision suggests they were born from the very first stars. If some of those primordial giants collapsed without exploding, they may have left behind black hole seeds that slowly grew, feeding on gas and merging with one another over cosmic ages. Another possibility points to vast clouds of gas in the early universe, collapsing whole and unfragmented, forming enormous black holes in a single dramatic act. However they arose, these entities became architects of galactic destiny. When matter falls toward a supermassive black hole, it does not vanish quietly. It heats, glows, and releases staggering energy, sometimes powerful enough to drive gas out of an entire galaxy and silence the birth of new stars. This process, known as active galactic nucleus feedback, is believed to be one reason the largest galaxies eventually went dormant. In the local group, these central black holes are calm, their fires dimmed by a lack of fuel. Yet the past was different. Both the Milky Way and Andromeda show signs that their cores once burned brighter. Gas was more abundant and easily consumed. In the far future, when the Milky Way and Andromeda finally merge, their central black holes will spiral together as well. That union will shake space-time itself, releasing vast gravitational waves. Today's detectors are too limited to sense such slow, deep ripples. But future observatories like Lisa may one day hear similar mergers echoing across the universe. Galaxies, however, are not sealed sanctuaries of stars. They breathe. They draw in gas from their surroundings and expel it back again. The space between galaxies is thin but not empty, filled with diffuse hydrogen heated to extreme temperatures by ancient shocks and radiant energy. This intergalactic medium feeds galaxies through a steady inflow known as gas accretion, replenishing the fuel required for star formation. Without it, galaxies would fade into stillness. Gas arrives in different ways. In one path, it is shock-heated as it enters a galaxy's dark matter halo, cooling slowly before settling into the disk. In another, colder streams flow along the hidden filaments of the cosmic web, delivering material directly and efficiently, especially in the early universe and in smaller galaxies. At the same time, galaxies lose gas. Stellar winds and supernova hurl matter outward, sometimes fast enough to escape entirely from small galaxies whose gravity cannot hold it. Larger galaxies reclaim much of what they lose. Gas driven into the halo eventually rains back down, forming a vast galactic fountain that cycles matter between disk and halo over millions of years. Even gas stripped from dwarf galaxies by tides or pressure does not vanish. It becomes part of the intergalactic reservoir waiting to be claimed again. Beyond stars and gas, galaxies are threaded with unseen forces. Cosmic rays particles accelerated to near-light speed and supernova shocks race through galactic space, guided by magnetic fields that weave through gas and stars alike. These high-energy travelers collide with atoms, producing gamma rays and neutrinos, heating and ionizing the gas they encounter. In subtle ways, they help regulate how readily clouds collapse and stars ignite. Together, black holes, gas flows, cosmic rays, and magnetic fields form an unseen council guiding galactic evolution. They are the hidden hands shaping when stars awaken, when galaxies fall silent, and how the chosen structures of the cosmos endure across time.